Hey everyone, hope y'all are all doing well. I thought I would go ahead and record this video finally, now that I can actually talk a little bit to go over the stuff we would have went over in class on Thursday. So this section covers linear regression models. So let's just start from the top. So a linear regression or a best fit line is a line that best describes the relationship between a independent variable and a dependent variable. So usually whenever we're doing this, we're looking at a scatter plot of data. We have the independent variable is on the x-axis and the dependent variable is on the y-axis. And we usually write the regression line in the form y of x equals m times x and then plus b, where the coefficient of x is the slope of the line and the constant term, the b, is the y-intercept. So the y-intercept is just the value of y whenever we plug in x is 0. So there are some key ideas behind these linear regression lines. So the first one, the regression line does not pass through all the data points. Not every data set we get is going to have an exact linear regression line. It's going to have an approximate one. There will be some instances when the regression line does actually pass through all the data points, but 99.9% of the time that is not going to happen. The regression line is chosen to make the distance between the data points and the line as small as possible. So a term that we use in statistics is we're trying to minimize the sum of the squared residuals, and the residual is the distance between the data point and the actual regression line. So we use the regression line to predict values of y for given values of x. So say we want to know what the predicted value of y is, but we don't have that particular value of x in our data set. We can try to use this regression line to predict that y value given the value of x that we want to plug in. So let's look at the first example. So suppose we collect data on study time, which is measured in hours, and quiz score, which is measured in points. And we want to use these 3 data points to create a regression line. So since I'm not in class to show you on the document camera how you do this on the calculator, what we're just going to do is do it in Desmos. So here I need to, I'll show you first how I create these things. So you're going to go up here and you're going to hit add item and you're going to go to table. And what you're going to do here is you're going to have a list of x values and a list of y values. So here in this first column, I'm going to put in the different values of my x's for those ordered pairs. So the x values were 2, 5, and 6. And then I'm going to go in and put the y values, which were 4, 7, and 8. And you have to make sure that these match up with the ordered pairs you have. So this first ordered pair was 2, 4. The second was 5, 7. The third was 6, 8. And this little magnifying glass here, the zoom fit, this will make it where you can see all the data points in a good window. And now what I can do is add a regression by clicking this thing in the top left-hand corner of the box, hit add regression. And by default, it's going to put a linear regression on here, and that's what we want. So what is our slope here? Our slope is 1, our y-intercept is 2. So that means we can write our regression line back on our notes. So let's go back to the notes here. Write our regression line that has the form y of x equals 1 times x and then plus 2. So here the slope represents the change in quiz score per additional 1 hour of study. and then the intercept represents the predicted quiz score when x equals 0 hours, so when someone doesn't study at all for the quiz. So let's look at another example. So this is another linear regression. It says, suppose we collect data on advertising spending and weekly sales in hundreds of units. So here again, we're going to do the same type of thing. We're going to plug these data points into Desmos, and we're going to do a linear regression. So something that you can do is this. Since you already have this table in here, what you can do is just change the values that are in the table. So I'm going to change it to the new ones I have now. So my first ordered pair is 2, 3. My second ordered pair is 3, 6. My third ordered pair is 5, 7. And my fourth ordered pair is 7, 6. So what do you notice? That as I did that, as I changed those values, it updated this linear regression equation down here. So here I'm going to take this, I'm going to round these coefficients here of the slope and the y-intercept to 3 decimal places for each of those. So going back to the notes, we're going to round each of those coefficients to 3 decimal places. So the slope to 3 decimal places is going to be 0.508. The y-intercept is going to be 3.339. So the slope tells us how many weekly sales we gain in this case. The reason it's gain is because the sign of the slope here is positive. So that means we're actually gaining for each additional $100 of advertising spent. So one little thing, if you go back here to Desmos, whenever you do a linear regression, it gives you this thing down here called R. So this R that's under the statistics thing here talks about the correlation coefficient. So the correlation coefficient, which is denoted by lowercase r, measures the strength and the direction of the linear relationship between the two variables. So there's a couple things about R that you need to keep in mind. It's always between -1 and +1. Whenever R is greater than 0, it means there's a positive linear relationship. R less than 0 means there's a negative linear relationship. And whenever we take the absolute value of R, if it's close to 1, it means there's a stronger linear fit. And whenever we take the absolute value of R, if it's closer to 0, it means it is a weaker linear fit. So what we want is, whenever we take the absolute value of R, we want it to be pretty dang close to 1. Sometimes we will get what is called a perfect linear fit. So a perfect linear fit occurs when the absolute value of R is equal to 1. So this could occur whenever R is equal to -1 or when it's equal to +1. So when it's equal to -1, it means that our linear regression line has a negative slope like this. And it means all of the data points lie exactly on that line. If R was +1, then it means we have a positive slope to our regression line, and that all of the data points lie on that line as well. So let's look at example 3 here. So this one, you don't actually need to consider the 3 data sets here, because we're not going to calculate R for these ones. We're going to calculate R for the next 3 data sets in example 4. So I just want to make this quick little remark here. So the data set with the strongest linear trend has the largest value of the absolute value of R, and the data set with the weakest linear trend has the smallest value of r. So with those two ideas in mind, what I want to do is now go to example 4, where I have to look at these three data sets here and say which one has the smallest value of r in absolute value, which one has the largest value of r in absolute value, and is there one that actually has a perfect fit, so when r is equal to plus or minus 1. So let's go back to Desmos now and type in these data values real quick. So I've already got one table entered in. So to do these other two tables, I'm going to go down here to where it says 2, and I'm going to do plus table, and then I'm going to go down here to where it says 3, click in here, and then do plus table. Now I'm just going to change these values in here. So here, this first ordered pair is going to be 2, 4. And then the second one is going to be 3, 3. The last one will be 4, 4. So here, this first thing corresponds to whenever we have the data set D. So we have 2, 4, 3, 3, and 4, 4. So here, notice that R is actually equal to 0 for this data set. Now let's go to data set E. Let's enter the data in for that. So here we have 1, 8. Then we have 3, 2. We have 5 and 6. Now, you can't really see these data points very well, possibly, but what we're going to do is all we want out of this is the value of R. So here, notice that R is equal to negative 0.32. So it's greater in absolute value than the first one, but it's still not very close to 1 in absolute value. So what I want to do is try the third data set, F. So this is going to be 2, 2, and then 5, 5, 8, 8. And then here, I want to add the regression again. So this one here has an R value of 1. So this is the largest R we're going to get an absolute value compared to the other two. So if we go back to our notes now, so this one here, data set D, this one had a R value of what? So let's go back here. Data set D had an R value of 0, right? So this one had R equals 0. This one had R equals 1. So that means based off of this, the set with the best fit is F. And the set with the worst fit is D. So, and here we have this little note. A perfect fit happens when every point lies exactly on the linear regression line. Or if you want to be matching up with the terminology from the very beginning of the notes, it was called the what? I think it was called the best fit line. Best fit line, yes. That could be another thing you could put right here equivalently. The best fit line. Either one of those would work. So we've talked about slope and rate of change before, but we're going to introduce it again. So for a linear function, f of x equals mx plus b, the constant m is the slope of the line, and the slope of the line represents the rate of change of the function with respect to x. So here, if m is greater than 0, then our function is increasing. So that means we have a positive slope. And if m is less than 0, then our function is decreasing. So slope can be interpreted as, if you want to think of it in terms of x and y, this is change in y over change in x. So if we, for instance, have two ordered pairs like x1, y1, and x2, y2, then the slope for this m would be found by the change in y, which is y2 minus y1, divided by the change in x, which is x2 minus x1. You've probably seen this formula before. So let's move on to example 5. It says, suppose the quantity of lettuce harvested is modeled by the following, where x is the number of inches of rain, and f of x is the quantity of lettuce in 100 pounds. So here, the slope is the coefficient in front of the x, which is 3. So m is 3. So the quantity of lettuce harvested is now here. This 3 is positive, so it's increasing by, so here it's increasing by 3. And remember, what are the units? It's 100 pounds. So 300 pounds per inch of rain. And f of 0 represents the quantity harvested when 0 inches of rain fall. And if we want to compute f of 0, all we do is plug in x as 0, and we get back 10, and this would be 1,000 pounds. So we'll just put 1,000. That's equivalent to 1,000 if you want to convert it to that, but that's okay, leave it like that. So let's go to another example where we're looking at the slope. So suppose the production of steel cable is given by this formula here, where X is the amount spent on raw materials. And usually when we're talking about cost, it's going to be measured in dollars. And F of X is the length of the cable, and this is going to be measured in feet. So here our slope is 150. The interpretation of this is the production of the cable is, again, this 150 is positive, so this will be increasing by, and here we have the slope, 150 feet per dollar spent. And f of 0 represents the amount produced when $0 are spent. And in this case, there is no y-intercept here, so f of 0 is just 0. So all we have here is just this 150x. There's no plus anything after the 150x, so the y-intercept there is just 0. So sometimes we can get linear trends from a graph too as well. So here we have, for example, 7, let G of T be the retail sales of natural gas to residential consumers, where T is the year between 2010 and 2018. So on this graph, the blue dots are the observed data, and the red line is the approximate linear trend, or this is the best fit line. So here from the graph, we can see that the sales appear to be linear in shape. So we'll say they appear to be linear. And what we can actually find is get a rough estimate of the slope by picking out 2 points that are on this. So here, we'll take, for instance, the 2 points 2011, 12, and 2017, 13.5. Then we can estimate the slope to be the difference in the y values, the 13.5 minus the 12, divided by the difference in the x values, the 2017 minus the 2011. And if you actually calculate this, this is 1.5 in the numerator divided by 6. This is 0.25 billion cubic feet per year. So now our interpretation of this would be the retail sales of natural gas were, again, the slope is positive, so this would be we're increasing by about, now we put the slope here, 0.25 billion cubic feet per year. Now, we can also interpret just single points that are on this scatter plot as well. So here it says if G of 2016 is approximately 13.0, then in the year, so remember the year was the x coordinate, so it's this piece right here. In the year 2016, the sales were about, now here's the y value here, 13.0. 13 billion cubic feet. So now we can also build linear trends from two different data points, for instance. So think of it this way. When you wanted to create a line, you can just use 2 points and use point slope form if you don't know the y-intercept. So let's look at this one. Suppose for a certain population, the average number of books read per person per year is 18 books in 2012 and 2020. So it says let X be the years since 2000 and B of X be the average number of books read per person. So here, whenever X equals 0, we're in the year 2000. And in the year 2000, each person reads on average 18 books. And then what's the other year we have? In the year 2020. So this would be an X value of 20. And then we have the corresponding average number of books is 12. So then we can find the slope by looking at the change in y values divided by the change in x values. So our change in y values is going to be 12 minus 18. Our change in x values is going to be 20 minus 0. And if I do this, this ends up being, up top we have -6, down below we have 20. So this would be, if we're using decimals, -0.30. So this is the first slope that we have done so far that is negative. So the interpretation behind this is the reading rate is, in this case, it's decreasing, actually, because the slope is negative. Decreasing by about 0.30 books per person per year. Now, we can write the model. So here we know the slope already. The slope is -0.30. Now we need to figure out the y-intercept. But we already know the y-intercept actually, because here x is 0 and the value of y is 18. So that implies our y-intercept here for this model is 18. So here in the next part, we want to do this prediction piece, right? So here it says to estimate the average in 2030, we use X is. So remember, X is the number of years since 2000. So if I'm in the year 2030, then that's 30 years since 2000. And I want to plug in 30. So B of 30. So I just plug in 30 right here and for X. Right, let me show you where, right here. And when you end up doing that, you'll get 9. So that means in the year 2030, the estimated number of books a person is going to read per year is 9. So you can also construct a linear model from a table of data, and that's kind of what we did in the first couple of examples, right? We looked at ordered pairs, which can be organized into a table, and then made a linear model based off of that. So here, let's look at example 9. It says, at an apple packing facility, 50,000 pounds of apples are processed per hour. The inventory AT in 1,000 apples over time, T in hours, is given below. So it says use 2 points. So we want to use whenever T is 0. So when T is 0, the value of A of T is 50. So here we're going to have 50. And then whenever t is 1, we have 30. So this will be 30. There we go. Now we want to find the slope. So to do that, we're going to look at the change in y values. So our ending y value is 30. Our starting is 50. And then we have our change in x values down below. Whenever I simplify this, this is negative 20. So negative 20,000 pounds per year. So now we know the slope, right? The slope is negative 20. So that's the piece that's going to go right here in the model. But we also know the y-intercept, right? Because whenever t is 0, we have that a of t is 50. So that means that our y-intercept then for this model is going to be 50. So let's put that down here. Now it says use the model to estimate the inventory after half an hour. So if I do that, I'm going to plug in 0.5 right there where I see a t. And when I do that after simplification, I end up getting 40. Now this last part right here is a little just tricky. It's just kind of connecting the words to the table. So it says the amount sent to another part of the plant in the first hour is the initial amount minus the amount at t equals 1. So if I look at the initial amount, that was the 50, right? And then after an hour, I'm at 30. So what's the difference between 50 and 30? It is 20. So this last one here we're going to go through goes over depreciation. So it says you bought a used laptop in 2018 for $1,200. In 2022, it is worth $600. Assume the value decreases at a constant rate. So that means every additional year you have the laptop, it keeps going down in value by the same amount each year. So here are the data points. Here we have the year, then the value. So in the year 2018, the value was 1,200. And then in the year 2020, it was 600. So let's look at the slope. We're going to take the 600 minus the 1,200, divide by the difference in the years. And when I do that, I end up getting negative $150 per year. So again, this slope is negative. So that means that the value of the laptop is decreasing by about $150 per year. So now we're going to do something a little different. We're going to change what our actual thing we're looking at is. So here we were given the years originally, right? We were given 2018 and 2022. Now we're going to convert this to years since 2018. And this will make it easier because whenever I convert to years since 2018, then this 2018 here becomes a 0 and 2022 becomes a 4. Because what do I already know? I already know the slope, right? The slope is negative 150. But once I make this conversion to years since 2018, then now I actually know the y-intercept, right? The y-intercept is right here. It's 1,200. So here, where the intercept is the value when y equals 0, or the value of the laptop in the year 2018. Sorry if you can hear my cat. She's meowing because I shut the door. And then this last piece over here, the change in value over 1 month is approximately the yearly rate divided by, in this case, we have 12 years in a year, so it'd be divided by 12. If you want to know what that actual value is, we can take the slope value of negative 150 and divide it by 12. That'll give us negative 12.5. So that means that every additional month we have that laptop, the value of that laptop decreases by 12 $8.5 each month. All right, well, hopefully that video will help you finish up the homework for the second section of notes. And I hope to see you all back in class on Tuesday. Y'all have a good night.